You've heard this before, but it bears repeating. Carbon is the element of life. So much so that when we explore other planets, the first thing we look for is compounds that contain carbon. In fact, there was a time when we thought that carbon compounds could only be produced by living things. So early chemists called them, as we still do today, organic compounds. Scientists back then considered biological molecules to be almost mystical in origin, until 1828 when German chemist Friedrich Wöhler discovered that urea, a component of urine, could be synthesized simply by heating ammonium cyanate, an inorganic compound. That proved biological molecules were just chemicals that could be created and manipulated in the lab. Suddenly, a new branch of chemistry was born. Organic chemistry. It's like my favorite chemistry. So what is it about carbon, though, that makes it so special? Well, a lot of things. Like silicon, which we talked about a few weeks ago, carbon is in group 14 on the periodic table, and like all of the elements in that group, it has 4 valence electrons. And in carbon, those 4 electrons can bond to other atoms in a really promiscuous number of configurations to form all kinds of structures. Which is why carbon is to biology what silicon is to geology. Just as silicon forms the basis not only for sand, but also most of the rocks on Earth, carbon is the foundation of most biological molecules. Really all biological molecules, right? Yep. The simplest organic molecules are pure hydrocarbons containing only carbon and hydrogen. Hydrocarbon. And they are where we're gonna start our 6-week exploration of organic chemistry. And they're a good place to start, partly because they play by the most straightforward rules. When all carbons in a pure hydrocarbon are bound to the maximum number of atoms, 4 atoms each, so that there are no double or triple bonds anywhere, these compounds are considered to be full, or saturated. That means that all the carbons have 4 bonds, either with other carbon atoms or with hydrogen atoms, in which case the hydrogens are bound to 1 carbon. No questions, no exceptions. These are the simple rules that govern some of the world's most useful, or at least used, compounds, the hydrocarbons that we use as diesel fuel, gasoline, methane, propane. You're gonna learn what these and other compounds look like, what their names mean, and how they take part in the reactions that fuel our lives. Welcome to organic chemistry. The fully saturated hydrocarbons I just described are usually called by the much simpler name alkanes. The simplest of the alkanes is one you've heard of before, methane, or CH4, the main compound in natural gas. The next simplest alkane contains 2 carbons side by side, each one of them is bonded to 3 hydrogen atoms. This is ethane, C2H6, another gas, and it's mostly used in the production of plastics. If we add another carbon and enough hydrogens to fill all those spaces, we get our next alkane, propane, C3H8, also a gas at room temperature and normal atmospheric pressure. Propane is a common fuel for cooking, heating, and vehicles, as well as a propellant for everything from aerosol cans to paintball guns. And we could do this all day, adding carbons to the chain and giving each compound a name, but that would be pretty boring. Things get more interesting though with the next alkane, butane, C4H10, because there are 2 different forms of it. The first is what you'd expect, just a chain of carbons with hydrogens stuck wherever they're needed to make each carbon have 4 bonds. This is called normal butane, or N-butane. But you can also arrange the 4 carbons differently by making a chain of 3 and then branching the 4th one off the center of the chain. This is called isobutane, or ibutane, and even though it has the same chemical formula as N-butane, its structure gives it different properties. For example, N-butane boils at negative 0.5 degrees Celsius, while isobutane boils at negative 11.7 degrees Celsius. These different structures for compounds that have the same molecular formula are called isomers. As you add more and more carbon atoms to the molecule, there are more and more ways that you can arrange them. So the number of atoms in butane only allows for 2 isomers, N-butane and isobutane. But pentane, or C5H12, has 3 possible isomers, and C6H14, known as hexane, has 5. Again, I could do this all day. Looking at this table of the number of possible isomers, you can see that escalated quickly. The takeaway here is that molecules with the same mass and number of atoms can form different structures, and as their structure changes, their properties also change. As a general rule, the larger and more complex alkanes are, the more densely their molecules can pack together, which means that they tend to be liquid or solid instead of gaseous at room temperature. So alkanes with main chains of 5 to 18 carbon atoms, like octane and gasoline, are liquids at room temperature, and those with more more than 18 carbon atoms, like paraffin or other waxes, are solids. Now you're probably picking up on a lot of words that you've heard before, even outside of chemistry class: octane, propane, methane, paraffin, so on. You can chalk that up to the enormous popularity of these compounds in our daily lives. Like I said, hydrocarbons are super useful because of the types of reactions they can take part in, which I will explain more in a bit. But first, I think it's high time you know what these names actually mean. Much like the general language of chemistry that we talked about months ago, organic nomenclature has its own system of prefixes, suffixes, and numbers that tell you what's in the compound being named. Now you gotta know the prefixes because they indicate how many carbon atoms are present. Here's one that I know you've heard before: meth. Meth in a name always indicates a molecule or branch containing one carbon atom. So the difference between amphetamines that doctors prescribe and methamphetamines that are sold on the streets is that methamphetamine has a methyl group, CH3, with one carbon, where amphetamine just has a single hydrogen atom. Hopefully that's helpful to you. Don't do drugs. Eth, meanwhile, indicates two carbon atoms. Prop means 3, bute means 4. From there, most of the prefixes will be familiar from geometry class, and you can review them in tables and learn them. I'm not gonna go through it all. Now, there are a few naming rules that are specific to alkanes. First, alkanes are always named based on the longest possible continuous chain in their structure. For example, even though this looks like a 5-carbon chain intersecting with a 6-carbon chain, it actually contains an 8-carbon chain if you look at it close enough. So this is considered an octane, with the 2-carbon chain attached to one of its carbon atoms. When shorter carbon chains are attached to longer ones like this, they're still named using the same prefixes, but we stuff a little YL onto the end to show that they're just attachments. Since this attachment has 2 carbons, we call it an ethyl group. And the attachment with just 1 carbon that turns amphetamine into methamphetamine, that's a methyl group. Attachments are also given a number to show you where along the chain they're attached. The long chain is always numbered carbon by carbon in the direction that gives the attachments the lowest numbers possible. So if we number the chain the right way, the ethyl group will end up at position 4, but if you do it the wrong way, it's in position 5. Low numbers win, so it's numbered from left to right in this case. So when we put it all together, this compound is called 4-ethyl-octane. Congratulations, you just named an organic compound. Now, particularly astute and studious students will have noticed something here. Earlier, I introduced you to isobutane, a compound with 4 carbons that were not all in a chain. We call that isobutane, and it is an isomer of butane, but according to these all-important rules of nomenclature, it's not actually any sort of butane at all. The longest carbon chain is just 3 carbons long, so it's propane, with 1 methyl group sticking off of it. If we wanted to give a technical name to it, isobutane would be 2-methylpropane, though since the second carbon is the only place where the methyl group can go without the molecule once again becoming butane, proper chemists just drop the 2 and call it methylpropane. Now suppose you have more than one of the same size group attached to the same chain, like 2 methyl groups on the same alkane. In this case, you put a number for both of them, and then prefixes like di and tri are used to indicate the multiple attachments. So for instance, if an octane chain has methyl groups attached to its 2nd and 5th carbons, it's called 2,5-dimethyloctane. On the other hand, if you have attachments of different lengths, you just name and number each one separately, being sure to list them in alphabetical order. So if the structure we just used had a methyl group on its 2nd carbon and an ethyl group on its 5th, it would be 5-ethyl-2-methyloctane. This is super useful for several reasons. One, because there are trillions of ways that organic compounds can come together, but also because you can work backward from a name and build a structural formula from it. Let's try that out. We're gonna build 4-ethyl-3,5-dimethyl-nonane. Start with the main chain, nonane. The prefix non indicates 9 carbons. Then add an ethyl group, a 2-carbon chain on carbon number 4, and then methyl groups, just 1 carbon on carbons 3 and 5. Our final step is to add enough hydrogen atoms to give every carbon atom 4 bonds, and now the molecule is complete. It's like a puzzle that we got to make. Of course, these compounds don't exist in isolation. Like any other compound, they can undergo a whole variety of reactions. But there are 3 types of alkane reactions that are important enough for us to cover right now, right here. The first is the kind that has made alkanes the most common fuels for combustion or burning. You'll note here that I'm saying burning. A common misperception, even among chemistry students, is that combustion somehow equals explosion. While that would definitely make things more interesting, also more dangerous. Those two things are not synonymous. Combustion is the type of reaction that powers your car and your propane grill, even candles, among many other alkane fuels. The general reaction for combustion requires a hydrocarbon, oxygen gas, and a source of heat energy. In this example, we're using methane, but it works the same for any pure hydrocarbon. The only thing that changes is the coefficients. The products of the complete combustion of a pure hydrocarbon are always carbon dioxide and water vapor. Just those two things. The next major type of reaction that alkanes experience is halogenation, when halogen atoms, like fluorine or chlorine, are substituted for one or more hydrogen atoms in the alkane. For example, the rather well-known compound chloroform is more correctly called trichloromethane. It's a molecule of methane that has reacted with chlorine gas, resulting in 3 of the hydrogen atoms being replaced with chlorine atoms. The final reaction type is dehydrogenation, and it, somewhat obviously, is the removal of hydrogen atoms from alkanes. For example, ethane can be dehydrogenated by this reaction, and as you can see, the result is that the carbon atoms are no longer saturated with hydrogen, thus requiring the formation of double or triple bonds to give the carbon atoms the 4 bonds that they need. Hydrocarbons that contain double and triple bonds have their own specific groups with different rules, reactions, and properties from alkanes, and those are the topic of next week's episode. For now, though, thank you for watching this episode of Crash Course Chemistry. If you were listening, you learned about some of the different classifications of organic compounds, the structures and properties of the simplest alkanes. You also learned about isomers and why they're important, how to name an alkane based on its structure, and how to build an alkane structure from its name. And finally, you learned a few important types of chemical reactions that alkanes experience: combustion, halogenation, and dehydrogenation. This episode was written by Edie Gonzalez, it was edited by Blake DiPastino, and our chemistry consultant is Dr. Heiko Langner. It was filmed, edited, and directed by Nicholas Jenkins. The script supervisor was Caitlin Hoffmeister, and Michael Aranda is our sound designer. Our graphics team, as always, is Thought Cafe.